Okay, so next I want to talk about ideality and solutions. Okay, and so in chapter 11, we're going to introduce the concept of an ideal solution, and we will define an ideal solution as being a solution in which all intermolecular interactions are exactly the same. So in an ideal gas, we assume that molecules don't interact and they don't take up space. In an ideal solution, we're going to assume that our molecules do take up space and they do interact, but we're going to assume that all of our intermolecular interactions are exactly the same. Okay, so we're going to define an ideal solution in which all of our intermolecular interactions are exactly the same. So now the basic idea would be so if I have a beaker of pure A, okay, so if I have a beaker of pure component A, and I think in terms of two body interactions, I will have AA interactions present in my system, right? So it's a homogeneous system in which A only interacts with A. If I have a beaker of pure B, okay, and I think again just in terms of two body interactions, okay, I'll have a homogeneous system in which B only interacts with other B molecules. So I'll just have BB interactions. All right, so now the idea is that when I have a system of pure A, you can think of A as being perfectly comfortable in solution. All right, so if I'm an A molecule, I'm in a solution with just other A molecules, so I am completely comfortable. Everybody's interacting with each other in exactly the same way. Everybody looks exactly the same. If I'm a B molecule in pure B, same thing. Everybody's interacting with everybody in exactly the same way. Everybody looks exactly the same. Okay. But now if I were to take that beaker of pure A, mix it with my beaker of pure B to form, okay, and so we can think of this as mixing at constant temperature and pressure, a mixture of A and B. So if I mix them to form a mixture of A and B, and I think again in terms of pairwise or two body interactions, now we'll have AA interactions, BB interactions, and I'll have cross interactions, AB interactions. Okay. So, if I think about pure A, okay, so you can think of this as an idealized state, right? If I'm an A molecule, I'm completely comfortable in my system of pure A. Everything's interacting in exactly the same way. I feel comfortable. If I'm a B molecule, my beaker of pure component B, okay, everybody's interacting in exactly the same way. I am completely comfortable. Okay, so now when I have this mixture of A and B, okay, I have AA interactions and BB interactions, right? So A interacting with A and B interacting with B. But now I have these cross interactions of A and B interacting. Okay, so if A is completely comfortable in pure A and B is completely comfortable in pure B, right? If we consider that, an idealized state for an A molecule and B molecule to be in, when we define our mixture, what we're going to do is we're going to define how comfortable I am in that mixture relative to these idealized states, pure A and pure B. Okay, so we're going to measure how my level of comfort in my mixture relative to those pure component states. Okay, so in an ideal solution, our A molecules and B molecules will be just as comfortable as they are in their pure component systems. Okay, so in order for A and B to be just as comfortable in our mixture as they are in those pure component solutions, what will happen is that we'll assume that our A and B molecules are A interacts with B exactly the same as A interacts with A and B interacts with B. So we'll assume that all of our intermolecular interactions are exactly the same. So you can think of it as A interacts just like B, right? A and B are one and the same, right? So that if I am a molecule in this mixture of A and B, I am just as comfortable in that mixture as I am in pure A and pure B. All right, so maybe you could think about A being a red molecule, B being a green molecule. All right, so they're tagged a different color, but everything else about them is exactly the same. Okay, and so when I'm A in this mixture, I'm just as comfortable if I'm A in a solution of just pure A, right? Everything's interacting in exactly the same way. I'm just as comfortable in that mixture as I am in pure A. Okay, so we defined an ideal solution as being a system in which all of our intermolecular interactions are exactly the same. Okay, so for this binary mixture case, my two components are just as happy in the mixture as they are in those two pure component states. Okay, or just as comfortable. All right. So, it stands then if an ideal solution is just a system which all of our intermolecular interactions are exactly the same. Okay, the pure component limit, right, when I just have, either AA or BB interactions in this case, that our system of pure A and pure B, right, in our pure component limits, we have an ideal solution. Okay. So cool. Ideal solution is going to be a mixture in which all intermolecular interactions are exactly the same. So our components are just as comfortable in that mixture as they are in those pure component systems. Cool. Now, next we're going to look at our properties of an ideal solution. Okay, and so what we're going to need to calculate these is we're going to need to know our property changes upon mixing in an ideal solution. And it just so happens that property changes upon mixing for an ideal solution are exactly the same as an ideal gas. So for an ideal gas, we're able to readily derive these, right, without a problem. But when it comes to ideal solutions, we're not going to derive them. But just take my word for it that property changes upon mixing of ideal solutions are exactly the same as that of an ideal gas. Okay, it doesn't mean that an ideal solution is an ideal gas, but the property changes upon mixing are the same. Okay, perhaps in an advanced course in thermodynamics, you could have the privilege of deriving those. Okay, but for now, we'll just take them to be the same. So, where are we getting at this? Well, if I let f be an arbitrary thermodynamic state function, okay, I know that I can write f as being equal to, okay, the molar average f of the pure component systems that I'm mixing together plus delta f of mixing. Okay, cool. Okay, all right, what is delta f of mixing? Well, and actually f I could equivalently write as sum over I xi f bar I. So f is molar average of pure component molar f's of those two, say in this case, systems I'm mixing together plus delta f of mixing, or equivalently, it's a molar average of the partial molar f's in that final mixture, right? So partial molar f being the effective f for component I in that mixture. So delta f of mixing then, right, it stands is equal to f minus sum over I xi fi. So it's the difference in my molar f of my final mixture relative to the molar average of the pure component f's of those systems I'm mixing together. Or equivalently, so if I match these two expressions, the term that I like is I can write this as sum over I xi f bar I minus sum over I xi fi, or collecting terms, this is sum over I xi f bar I minus fi. I like this because delta f of mixing I can see is the molar average of the difference in my partial molar f, which is the effective f due to component I in my mixture, minus fi, fi being pure component value at the same temperature and pressure. All right, so I haven't written the functional dependencies, but remember, when I think about property changes upon mixing, I'm taking two systems, or could be more than one system. So in this case, for the binary case, I'm taking two systems at the same temperature and pressure and mixing to form a final mixture at the same temperature and pressure. Okay, so this would be f at Tp and xi. So at this, given temperature, pressure, and composition, fi, my pure component values would be at the same temperature and pressure. Delta f of mixing, well, that's going to be a function of composition. So that's temperature, pressure, and composition of my final mixture. F bar I is a function of temperature, pressure, and composition, right? Because it's a function of the composition of my final mixture. Okay, so just to kind of write this out, so delta f of mixing, okay, we can write as sum over I xi f bar I minus fi. Okay. And yeah, we'll use that as our base. And then if we wanted to calculate f, okay, f could be written as sum over I xi fi plus delta f of mixing. Okay. So I mentioned that because what we'll do next is we'll recall our expressions for delta f of mixing in an ideal gas. And remember, property changes upon mixing for an ideal solution are the same as an ideal gas. And we'll use that to get expressions for f in an ideal solution. And then from there, we'll use the second expression to get expressions for the partial molar f's of our components in an ideal solution. Okay. All right. So our property changes upon mixing for an ideal gas, which will be equivalent to that of an ideal solution. Okay. So when I write our property changes upon mixing for an ideal solution, I'll put a superscript ID just as we had ideal gas before. And so remember, for an ideal gas, we had the delta V of mixing, okay, for ideal solution, okay, is going to be equal to 0. Delta H of mixing for our ideal solution will also be equal to 0. And delta U of mixing for our ideal solution will also be 0. Okay? And, it makes sense. So if we have a ideal solution which all of our intermolecular interactions are exactly the same, well, then it makes sense that delta U of mixing is equal to 0. Delta V of mixing, makes sense. So that would tell me then if all of my molecules are interacting in exactly the same way, you think about, volume or molar volume. So in a pure component system, it's, the hardcore volume, the space physically occupied by a molecule, plus this buffer region, right, in which no other molecules are present, right? It's the force field around that central molecule, okay? And so if all of my intermolecular interactions are exactly the same in my mixture as they are in those pure component systems, I expect that buffer region to be the same. Okay, so delta V of mixing 0, delta U of mixing 0, and so hence delta H of mixing is 0. Okay, cool. Delta S of mixing, so remember I told you should remember delta S. Okay, and so how you should remember delta S of mixing, okay, for an ideal solution. So the term that you should remember is sum over I xi log xi. Okay, now in terms of what's going to come next, okay, we'll talk about in a second, but the important term to remember is sum over I xi log xi. Okay, all right, so next in terms of the rest of it, what goes in the beginning, okay, delta S of mixing is always going to be positive. Okay, delta S of mixing for an ideal solution, just like for an ideal gas, will always be positive. Okay, so xi is always going to be less than 1. Right? So in the pure component limit, xi is equal to 1, you get delta S of mixing is 0, right? But you're mixing, pure A with pure A. That's not really fun, right? But in general, right, for a mixture, you're going to have that xi is less than 1. Okay, so xi is going to be between 0 and 1. So if xi is less than 1, log xi then will be negative. Okay, so xi is going to be less than 1, so log xi will be negative. Okay, so if delta S of mixing is positive, I know then I need a negative sign in front of here to make it positive. Okay, and it's going to be negative R, and R just comes in, and the R has the same units as S. So remember, G is equal to H minus TS. Okay, so G has units of energy, H has units of energy, T times S has units of energy, right? It's T times S that has units of energy. All right, so S has units of energies per temperature, per Kelvin, right? Same units as R. Okay, but let me erase that, just so I don't confuse you when I post these. Okay, delta G of mixing. Okay, I guess I shouldn't have entirely erased them, because if G is equal to H minus TS, right, and I'm mixing at constant temperature and pressure, delta G of mixing is delta H of mixing, minus T delta S of mixing. Okay, so delta G of mixing is a positive RT, sum over I xi log xi. Okay, so let me not erase these. We can keep these as an aside. Okay, So here are my expressions for the property changes upon mixing in an ideal solution, right? Which happen to be exactly the same as an ideal gas. Now remember, an ideal gas is an ideal solution because we said an ideal solution is a system in which all of our intermolecular interactions are exactly the same. So an ideal gas is an ideal solution, okay? But an ideal solution, not all ideal solutions are ideal gases, okay? Because we're just saying that all of our intermolecular reactions are exactly the same, not that they're zero. So an ideal gas is an ideal solution. An ideal solution is not necessarily always an ideal gas. Okay, so it should make sense that the property changes upon mixing for the two of them are exactly the same. So when it comes to entropy of mixing always being positive, okay, this is a combinatorial term. So if I think of a binary case where I'm mixing A and B, okay, so A and B are going to interact in exactly the same way. Okay, but they're going to be distinguishable. So if my A molecules are, say, all red, my B molecules are all green, I mix them together to form a final mixture of A molecules and B molecules that are distinguishable. So there's going to be more unique configurations available to my system. So if I were to switch the position of an A molecule and B molecule, I create a new configuration in my system. So this entropic term is entirely combinatorial. Okay. All right, so those are my property changes upon mixing, which are the same as an ideal gas. And hopefully you should remember those from the case of an ideal gas. Okay, so now we said we're going to use our first box in expression here to get our expressions for our properties of interest in an ideal solution. Okay, so we're going to do just that. So if I want to calculate the molar volume of an ideal solution, okay, well, delta V of mixing of my ideal solution is 0. So I'm just left with sum over I, xi, vi. The molar volume of my ideal solution is just molar average of pure component molar volumes of the systems I'm mixing. Just like H ideal, the enthalpy of my ideal solution is sum over I, xi, hi. U ideal is sum over I, xi, ui. Okay. Now remember, just for completeness, so I'll write it for this first case. When I say V ideal, right, we're talking about an ideal solution at Tp and Xi. Okay. When we talk about these pure component values, those are for pure components at the same T and P. Okay. Remember, I'm mixing at constant temperature and pressure. Okay. When it comes to Gi, okay, well, Si. So S of my ideal solution. Okay, let me bring that up so you can see that. The entropy of my ideal solution is going to be, okay, sum over I, xi, si, molar average of my pure component values. Okay, but now for S, delta S of mixing is not 0. Okay, delta S of mixing was negative R, sum over I, xi log xi. Okay, so this is molar average plus delta F of mixing. So plus, so it would be a negative R sum over I, xi log xi. Okay, cool. Okay, or if I wanted to group terms, that'd be equal to sum over I, xi, si minus R log xi. Okay, just want to collect terms. G of my ideal solution. Okay, so just as we said, delta G of mixing is always going to be positive, or delta S of mixing is always going to be positive. Delta G of mixing is always going to be less than or equal to 0. Right? It'll be equal to 0 in the pure component limit. Okay, but delta G of mixing then in general, well, delta S is always going to be greater than or equal to 0. 0 in the pure component limits. Delta G of mixing will always be less than or equal to 0. Okay. If I were ever to have a delta G of mixing that's positive, what that tells me then is when I mix those two pure component systems, okay, we're going to get phase separation. I'm going to separate to form two distinct phases. That's going to correspond to liquid-liquid coexistence. But once those two phases separate, I'm going to end up reducing the molar Gibbs free energy of my overall system compared to the case if they were mixed. Okay, so delta G of mixing, if it's positive, that means I'm going to get phase splitting. I'm going to have a partially miscible system. Okay, but anyways, getting back on topic. G ideal would be sum over I, xi gi plus RT sum over I xi log xi. Okay, remember I'm mixing at constant temperature and pressure. And if I want to group terms just like entropy, I can write this as sum over I xi gi plus RT log xi. Okay, cool. Okay, so there's my expressions then for my ideal properties, or my thermodynamic properties. So I'm just trying to get my cursor, trying to figure out where my cursor is. So those are my thermodynamic properties, expressions for my thermodynamic properties in an ideal solution. Okay, cool. Okay, so far it looks just like an ideal gas. Okay, so you said we'd use first box-in expression to get expressions for our properties in an ideal solution. We're going to use our second boxed-in expression to get expressions for our partial molar properties. Okay, and so what do I mean by that? Okay, let's see how much space we have here. Okay, well, we said that in general, delta F of mixing is equal to the molar average of F bar I minus Fi. Okay, molar average. Oh, let me rewrite it so I get some space. See, it'll be just like I'm on the whiteboard. Sum over I xi F bar I minus Fi. So it's the molar average in the difference of my partial molar F in my mixture relative to my pure component F. Okay. All right. So what we are going to do is up here we have expressions for our property changes upon mixing. Okay, got it. So what we're going to do is starting with V. Okay, so delta V of mixing in my ideal solution, okay, is going to be equal to molar average of V bar I in my ideal solution minus Vi. Okay, and delta V of mixing of an ideal solution is equal to 0. Okay, all right. So in order for these two expressions to be consistent with each other, okay, it must be that V bar I, my partial molar volume in an ideal solution, is just equal to Vi. Okay. Now, we won't bother with enthalpy and internal energy because they're exactly the same, but we'd also get that H bar I in an ideal solution, my partial molar enthalpy in an ideal solution, is just equal to Hi, and U bar I in an ideal solution is just equal to Ui. Okay, so there's my expressions for partial molar enthalpy, internal energy, and molar volume in an ideal solution. Right, the partial molar value is just equal to the pure component value. And again, we said the fact that those property changes upon mixing were 0 made sense because we're assuming that the molecules are interacting in exactly the same way in the mixture as they do in those pure component systems. Okay, but of course this isn't going to be exactly true for entropy in molar Gibbs free energy. Okay, and so we'll get to that. So in terms of entropy, okay, so delta S of mixing in my ideal solution is by definition molar average of S bar I in my ideal solution minus Si, and that is going to be equal to minus R sum over I xi log xi. Okay, and so what I'm going to do next, okay, just so it makes it easier to equate, is R is constant. Okay, actually negative R is constant, right? It's just my molar gas constant. So I can bring it into my sum. Okay, so I can write this as, let me just rewrite the first term. Okay, so negative R is constant, so I can bring it in my sum. And I can write this as negative sum over I xi minus R log xi. Okay, All right, so in order for these two expressions to be consistent and equivalent with each other, it must be that my terms in parentheses are equivalent. Okay, so it must be that S bar I ideal minus Si is equal to minus R, or negative R, log Xi. Okay, so therefore, S bar I ideal is equal to Si minus R log Xi. Okay. So now this is cool, right? So why I say it's cool is we said Xi is always going to be less than 1. So log Xi will always be negative. So this term is going to be positive. Okay, so it must be that S bar I ideal minus Si is greater than 0. So therefore, it must be that Si ideal is greater than Si. So the partial molar entropy of component I in my ideal mixture is greater than the pure component entropy at the same T and P. So write out functional dependencies. So S bar I in an ideal solution at Tp in Xi is going to be greater than Si at T and P. So the effective entropy of component I in my ideal gas or my ideal mixture or my ideal solution is greater than in a pure component system at the same temperature and pressure. Okay, the entropy increases. So in my ideal solution, it's purely a combinatorial effect because there's more unique configurations available to my system. Okay, cool. Okay, and so if I needed to calculate the partial molar entropy of component I in my ideal solution, it's just pure component value at the same T and P minus R log Xi. Okay, cool. So here's going to be my combinatorial term. Cool, right? All right. Now if we go to G, delta G of mixing in my ideal solution, by definition, sum over I Xi, G bar I ideal minus Gi, and that's going to be equal to, or must be equal to RT, sum over I Xi log Xi. Okay, so we're mixing at constant temperature and pressure. Okay, so this is constant, so I'm going to bring it in my sum, just to simplify matching, right, as you see the magic trick from last time. Okay, now we did exactly this when we talked about partial molar properties in ideal gases. And so hopefully, if it didn't make sense then, right, you're starting to see it here. Okay, and oftentimes thermo is that type of animal where you just have to keep seeing things in different ways to begin to make connections of things. Okay. So again, if these two expressions are equivalent and consistent, it must be that my terms in parentheses are equivalent. Okay, so G bar I ideal minus Gi is equal to RT log Xi. Okay, all right, so now we can play the same game too. So Xi is going to be less than 1, so log Xi will be negative. Okay, so I have the G bar I ideal minus Gi is going to be less than 0. So the G bar I ideal is less than Gi. So the partial molar Gibbs free energy of component I in my ideal solution, so the effective molar Gibbs free energy of component I in an ideal solution is less than pure component value at the same T and P. So what this would tell me is it's more favorable for, say, component A to be in a mixture with B than it is to be in, pure A, right? Why it's more favorable, right? And so this is where I need to be comfortable, or not comfortable. I need to be consistent in my terminology, right? In our ideal solution, all of our intermolecular interactions are exactly the same, okay? So an A molecule, from an intermolecular interaction standpoint, is just as comfortable in my mixture than it is in those pure component states, okay? It's more favorable to be in the mixture, right? It's preferred to be in the mixture. Why? Because there's more configurations available to my system, right? There's so Cincinnati Zoo doing the renovations now, there's going to be more room to roam, right? So there's more configurations available to my system, and so it's more favorable, purely from that combinatorial standpoint. Okay, so my partial molar Gibbs free energy component I in my ideal solution is less than the molar G in the pure component systems. And if I want to calculate G bar I ideal, my partial molar Gibbs free energy is equal to Gi plus RT log Xi. Okay, cool. So now we have expressions for UH, V, G, and S, so those property changes while mixing, expressions for those properties in an ideal solution, and now our partial molar properties. Okay, cool. Okay, and so that's the end of this section of the notes. I'm going to make one comment as a spoiler in terms of the next screencast, the next set of notes, and namely that is if I look at this expression or just equivalently this expression. Okay, when it comes to calculating fugacity in an ideal solution, okay, the key is going to be here I have a difference in molar Gibbs free energies, okay, and essentially this is Gi molar Gibbs free energy pure component I, but it's equivalent to the partial molar Gibbs free energy of component I in pure component solution. Okay, and so when I see differences in Gibbs free energies at the same temperature and pressure, then I know that that's going to be equivalent to RT log ratio of fugacities. Okay, and so how we get to an expression for fugacity of component I in an ideal solution is exactly from here, right? It'll be RT log Xi then is going to be equal to RT log ratio of fugacities. Okay, but we'll get that in the next set of notes just so you can see exactly where we're going to pick up and where that continues.